In this video, we are going to discuss the product and sum rules. These are two basic but important probability rules with a lot of different applications. As a brief summary, the product rule is applied to determine the joint probability of two or more independent events, whereas the sum rule is applied to determine the total probability of two or more mutually exclusive events. Each of these words will be explained in the next few slides. Let's start by looking at the product rule. If A and B are two independent events, then the probability of both A and B occurring is the product of the individual probabilities for A and B. In other words, the probability of A and B is the probability of A multiplied by the probability of B. Independent events mean that the occurrence of one event does not affect the occurrence of the other. So for example, if you were to toss a coin twice, then getting ahead in the second toss is independent of what you got in the first coin toss. The product rule can also be used for multiple independent events, in which case you would just multiply the probability of each of the independent events to get the total probability. Here's an example. Suppose that a randomly selected couple has two children of different ages. What is the probability that the first child is a boy and the second is a girl? Well, giving birth to a boy and to a girl are equally likely. In other words, their probabilities are the same. In other words, a half each. The gender of each child is independent of the gender of the other child. This means that we can apply the product rule, so that the probability of first child being a boy and the second child being a girl is the probability of the first child being a boy multiplied by the second child being a girl. In other words, half multiplied by a half, which gives a quarter. Now the sum rule. If A and B are two mutually exclusive events, then the probability of either one or the other occurring is the sum of the individual probabilities for A and B. In other words, the probability of A or B is the same as the probability of A plus the probability of B. Mutually exclusive events means that the events cannot both occur at the same time. For example, Monday and Tuesday would be mutually exclusive, but Monday and April would not be. The sum rule can also be applied if you have several events as long as they are all mutually exclusive. In that case, just add each of the different mutually exclusive events to get the total probability of one of them occurring. Here's an example of the sum rule. Suppose that in country X, 47% of the population has blood type A and 20% has blood type B. What is the proportion of the total population that has either blood type A or blood type B? Well, each person can only have one blood type. This means that having blood type A and having blood type B are mutually exclusive events. This means that we can use the sum rule. In other words, the total probability is given by adding the two different probabilities. 47% plus 20% is 67%. Now let's have a look at a longer example that involves both the product and the sum rules. Suppose that Kate and John have these given genotypes in 3 genes, where a capital letter represents a dominant allele and a lowercase letter represents a recessive allele. What is the probability that their child will possess all 3 dominant traits? To have all 3 dominant traits, their child must have a phenotype that involves at least one dominant allele in each of the 3 genes. In other words, P dash could represent big P or big P small p, and similarly for the others. Each gene is independent of the others, so this means that we can use the product rule. In other words, to get the total probability, we need to multiply 3 independent probabilities together. This means that to solve this question, we need to find each of these 3 independent probabilities, and as a final step, multiply them together. First, let's find the probability of P dash. Remember that Kate has genotype big P, and John has genotype small p. We can fill these out in a Punnett square and fill out the different possibilities for their child. But notice that there is only one genotype possible for the child, big P, small p. This means that the probability of P dash is the same as the probability for big P, small p, which is equal to 1. In other words, 100%. So that was easy. Now let's have a look at the probability for big Q dash. Remember that Kate has genotype small q, and John has genotype big Q, small q. Again, let's fill out the different possibilities for their child in a Punnett square. This time there are two different possibilities. Since the child can only get small q from Kate, this means that the probability of this is 100%. However, from John, it could get a big Q or a small q with equal probabilities. So each of these has probability a half. The allele that is received from John is independent of that received from Kate. In other words, we should use the product rule. So to get the probability of Q dash, we would find the probability of big Q, small q, which is the probability of small q from Kate multiplied by the probability of Q from John. In other words, 1 multiplied by a half, which is equal to a half. Now let's find the probability of R dash. Each parent had the same genotype, big R, small r. So this time, filling out the Punnett square, we see that there are 3 possible genotypes for the child. Let's try to find the probability of each of these 3 different types. Notice first that from each parent, receiving a big R or a small r is equally likely. In other words, each of them have probability a half, which we can fill out in the table. Also, the allele that is received from Kate is independent of that from John. In other words, we should use the product rule. If the child is going to have genotype big R, this means that it must have received the big R from each of the 2 different parents. Because these are independent of each other, this means that we should multiply the 2 different probabilities. And a half times a half is equal to a quarter. Similarly, the probability of getting a big R from the mother and a small r from the father is the same as big R from the father and small r from the mother, and each of these is a half times a half, which is equal to a quarter. So we can fill all of these out in this table, and also similarly small r is also a quarter. Now that we have filled out all the probabilities in this table, we can put this together and find the probability of R dash. The probability of getting a big R from the mother and a small r from the father, compared to the other way around, are mutually exclusive events because they cannot both happen in the same child. This means that we can use the sum rule. In other words, to find the probability of big R, small r, we should add a quarter plus a quarter to get a half. Similarly, the different genotypes are mutually exclusive events because they cannot happen in the same child. This means that we can add these probabilities. A quarter plus a half is equal to 3/4. Now we can finally put all this together to answer the final question, which was, what is the probability that the child will possess all 3 dominant traits? Notice that so far we've worked on 3 completely separate steps to find these 3 different probabilities, and only now can we start putting this together. The formation of the genotype for one gene is independent of the other genes. This means that we can use the product rule. So to find the total probability, we should multiply the 3 probabilities that we found in step 1, 2, 3. 1 times a half times 3/4 gives us 3/8, and this is the final answer. Here's a summary with the question and the final answer and some of the important probabilities that we computed along the way.